Hi everybody, welcome back. In this video we are going to continue on looking at how we can handle differences in the structure of the data in linear regression. So in the last video we looked at what happens if the units are changed. So if you look at say dollars versus thousands of dollars, or a whole number percentage versus a decimal percentage. In this video, we're going to start looking at the nonlinearities in the parameters. So in the beta, in the functions of x. We still have linear parameters in terms of, we have linear parameters for the betas. So like y is equal to beta 0 plus beta 1 x squared will give us a quadratic plus the error term. And y equals beta 0 plus beta 1. So this addition here means we have a linear regression, but we have a nonlinear function of x. And so here we could have something like log of x plus epsilon. And so in this video, we're going to look at quadratics and why we might use a quadratic term in a regression equation. And then the next one, we'll go on to logs. But actually, most of the time, whenever we're using quadratics, we're probably using two variables, both x itself and x squared plus the error term. So anyway, we're gonna start with quadratics and we're gonna look at that. So quadratics. Ultimately, the reason why you might consider using quadratics or log functions is you have to think about the data and think sort of intuitively about how this phenomenon that you're trying to model would look in real life. And so to give an example, let's take a model looking at wages. And let's look specifically at how experience affects wages. So if this is the model itself and this is all we have, then what we've got is we're going to have something that looks like this. I'm going to abbreviate experience, and we have wage on the y-axis. And so here we have 0 years of experience, 1, 2, on up, right? And so let's say the intercept starts here maybe, and as you have more experience, your experience increases, or your wage increases, and it is just a linear function that continues on linearly indefinitely. So with 1 year of experience, let's say the slope intercept, or the intercept of the regression line, let's call that, let's say you've graduated college, you come out of college with 0 years of experience, and you get yourself a job paying $50,000. Okay, then with a year of experience, let's say that these are going up in intervals of 30,000. So after a year, you've got 30, or you've got 80. After 2 years, you add 30 more, you're at 110. That's too much. Let's do 60 and then 70, right? And then you go on out, and after 20 years of experience, you've added $20,000, or no, you've added $200,000. And so now you're at $250,000. After 30 years, you're at $350,000. And after 40 years, you're at $450,000. After 40 years, you are probably now at least 65, maybe 70. Let's say you keep working. After 50 years, this model would assume that your wage is now $550, and now you're 80 years old, right? And essentially, the problem with modeling experience like this is that, in general, these first, say, 5 to 10 years of work are typically the time period in a career where you see the largest wage increases. And as you start reaching the end of your career, it's going to start slowing down. And so what your real wage might look like is something that starts going up but then slows, and then maybe even starts turning down as you retire. Actually, it might even turn down quickly, but we'll keep it kind of nice and smooth. So this blue line is a quadratic function, and that can be modeled by adding a squared term into the equation. So the blue line, which is going to be more realistic, could be modeled like beta 0 plus beta 1 times experience plus, which actually in practice, especially for wage equations, the beta 2 is going to be a negative number, times experience squared plus the error term. And so what that's saying is that experience in this kind of first derivative, experience is increasing, but it's increasing at a decreasing rate. So it's still going to be going up, but it's going to be going up more and more slowly over time. Okay, and so the way that we can do this is we accomplish this. We accomplish a more realistic model by including a squared term. Okay, so this is going to be more realistic. What this is also saying is that beta 1 is going to be greater than 0. Beta 2 is going to be less than 0. That's going to say as experience, or let's say wage increases with experience, but at a decreasing rate. Alright, let's switch back to black. Okay, so the other thing is that we have to be a little bit careful now about the interpretation of beta 1 and beta 2. Because ultimately, the question that we're interested in is, how does y change when we change x? Or in this case, how does the wage change, the estimated wage, when we change experience? Okay, normally that beta 1 estimate is equal to what we're interested in, the change in wage with respect to the change in experience, ceteris paribus, holding everything else constant, but this ceteris paribus assumption, if we're only looking at beta 1, which is here, the interpretation of beta 1 means that any other control variable we might have, maybe we're also including something like years of education, maybe we're including things like gender, right? So like a male, female, dummy variable, and all these other ones. So beta 1 interpretation assumes the ceteris paribus assumption for everything else, but that everything else includes beta 2 experience squared. But you can't hold experience squared constant if you're changing experience. Mathematically, that just doesn't work. So the problem is, but it doesn't make sense to hold x squared fixed or a constant when changing x. Okay, and so, or it doesn't make sense to change experience when experience squared when changing experience. So we can use a little bit of math. If we had a generic formula here, beta 0 estimate plus beta 1 x plus beta 2 x squared. Ultimately, we can use a little mathematical manipulation, and if we want to look at that change in y, with respect to a change in x, that's going to approximately equal beta 1 plus 2 beta 2x. This little formula is quite important in terms of interpreting that marginal effect, the marginal change in y, or the change in y with respect to a marginal change in x. This formula here is telling us how we can interpret that when we estimate a beta 1 and 2. So in our example here with the wages, and we'll do this in Python, when we estimate that wage equation, we have beta 0 plus beta 1 times experience plus beta 2 times experience squared. When we estimate that, we'll get the following output. 3.73 for the intercept plus 0.298 times experience plus 0.0061 experience squared. Now, let me also just recall that this is the hourly wage. That'll matter for the interpretation. So again, wait a second. This plus here is a minus. Beta 2 is a negative 0.0061. So minus right here. And again, that's this idea that experience has an increasing but diminishing effect on wage, like this. Okay, and that intercept there would be the 3.73. Okay. All right. So the estimated effect, coming back to this formula here, estimated effect is as follows. So the change in wage with respect to experience is then equal to beta 1 plus 2 beta 2x. And we now have beta 1 and beta 2. And so we can actually calculate that out. So that's equal to 0.298 minus 2 times 0.0061. It's a minus because beta 2 is negative x. So now it's a function of what x is, because if experience changes, experience squared also changes. So if you want to interpret the output from a regression here, it actually depends on where you start. It depends on if you're going from 1 year of experience to 2, or 2 to 3, or 3 to 4, or 20 to 21. And so what I want to show you is how we can think about that. If you wanted to estimate or display the precise effects. So if we have x here, and we want to look at the change in wage, estimated wage. So let's say we're starting at 0, and we're going to be going to 1 year of experience. Well, x is equal to 0. So the change in wage with respect to experience is 0.298 minus all of this, but it's times x is equal to 0. So minus 0. So that's equal to, and remember, wage again is measured in hourly wage, so it's measured in dollars. Going from 0 years of experience to 1 year of experience, we start with 0, and that's just going to be equal to 29 cents. So with no experience, you're starting out at basically 30 cents. Now x is equal to 1. So we're now moving from 1 to 2 years. And at 1, we go 0.298 minus 2 times 0.0061 times 1. Calculate that out. That's going to give us approximately 17 cents. 0.176 or 17.6 cents. Okay, so you could do that with any number of years of experience, and you can actually calculate that true effect. I'm going to do one more. If we start out here at 10, so you're going from 10, starting at 10 years, going to 11, you would do 0.298 minus 2, 0.61, 0.0061 times 10. That's going to come out to, oh shoot, that's the one that, sorry, I'm sorry. This, if you calculate that, that's what this comes out to. I'm sorry, up here, if you calculate 29 cents minus 0.0061 times 2, that's going to come out to 0.286 or 28.6 cents. Okay, and then you carry on, and then on the 10th year of experience, you're still increasing. So your experience is your wage is increasing by 17 cents, but it's increasing by less than what it was in the beginning. Okay, so so there you can kind of see this increasing but diminishing marginal effect. And we can actually calculate exact predicted changes in the wage based on at which x variable we start. So let me kind of summarize what we have so far. Oops. Oops. Okay, we can compute predicted changes directly. We can compute predicted changes in y, or in this case the wage, directly for any given x. But a lot of times we don't want to go through, we might have, this is a continuous variable. We might have dozens of possible values for x, if not hundreds. So we can also summarize some of the effects by using averages or quartiles. So we can compute predicted changes precisely, but for summarizing effects, it's common to use to compute changes in y from averages of x. So if the average years of experience was 10, say, well, actually, I'm going to write that example in a second. Oh, let me write it now. No, let me write it in a second. So from averages of x, we could also do quartiles of x. So for example, here you do the 25th quartile, the 50th, which would also be the median, or the 75th. And that way you could kind of see the effects across the possible distributions of wages. And you might see a larger slope, and then a smaller slope, and then a smaller slope still, based on that 25th percentile cutoff, and then the 50th, and then the 75th, and you would see 1, 2, 3, 4, and you could see those slopes for each individual quartile, and that slope there, and that slope, and that slope, and that slope. Yeah, so that's that's a possibility, and the way that you can think about it is, for example, if average x, or in this case experience in the sample, was 10 years, then the average effect is an increase of 17.6 cents. An increase of 17.6 cents in the wage for a 1 year increase in experience. Okay, and that 17.6 cents comes from here. Okay, so if the 10 was the average years of experience, then the average effect of experience on wage is 17.6 cents. But again, you might consider looking at multiple quartiles or quintiles or deciles or whatever you would want to do. And then you can just look at the average effect within that range of data. Okay, so in the end, it is useful, especially if you want to try to be a little bit more realistic about how you're modeling the variables in your equation. If you do think there might be some nonlinear relationship that has this diminishing marginal return or diminishing kind of marginal effect there, then adding a squared term could get you there. And yeah, in the end, you could do more analysis. Technically, a squared term is going to start dropping at some point. You can solve for this turning point. And yeah, so we won't get into the details of that, but relatively simple calculations there too. And so then you could start to look at optimizing policies or business practices. Yeah. So in any case, that is how we deal with squared terms and their a little bit special interpretation of the marginal effect of experience on wage if there's a squared term. So the next several that we're going to be talking about are incorporating logs into the models. Fortunately, logs are actually less complicated and they have even easier interpretations. Perhaps in many cases even easier than a normal, if you have a salary and that's a function of return on equity. Here return on equity changes, that's going to change by some dollar amount. Once we start adding logs in here, then some of these we're going to be interpreting them as percentages. And so that actually becomes very useful in many applications as well. Okay, so in any case, logs are up next. So stay tuned for that, and thank you for watching. I'll see you in the next video.